Preside of the Q&A. Okay, go for it.
Okay, so good afternoon, everyone, and welcome to the Electron Devices Society at Cornell. We are a student-run, faculty-guided group.
I'm sorry. Start your report.
Yes.
Thanks.
So we are a student-run, faculty-guided group, and our seminars cover topics ranging from electronics, photonics, and quantum devices, all the way to epitaxy, nanofabrication, and novel measurement techniques. This is the fourth talk of our series, and there are 4 more to go this semester. We are also starting to schedule speakers for the next semester. So if you would like to schedule a speaker in the coming semester, please reach out to us on this email address or reach out directly to one of the team members. For today's speaker, we have Dr. Scott Holmes. It is a pleasure to welcome you today as we gather to explore the exciting advancements in superconductor electronics and quantum computing. As we navigate the complexities of modern technology, the development of an effective roadmap is crucial to guiding our efforts in these cutting-edge fields. We are honored to have Dr. Scott Holmes with us, a leading figure in this arena. Dr. Holmes chairs the Cryogenic Electronics and Quantum Information Processing International Focus Team for the International Roadmap for Devices and Systems. His extensive experience, which includes pivotal roles at IARPA and DARPA, has positioned him at the forefront of innovations in superconductor technologies. Today, Dr. Holmes will share insights into the critical fabrication needs for semiconductor electronics, focusing on how we can enhance the scalability and complexity of digital circuits to meet the growing demands for applications in quantum computing and machine learning. Please join us in welcoming Dr. Scott Holmes.
Well, let me check. Is there a way to find out if the sound volume is adequate for everyone, especially those on Zoom? I hope you can hear me. Okay. One thing that Deb didn't mention is that I am a member of IEEE. I'm also an Electron Device Society member, and I serve on the IEEE Council on Superconductivity as the EDS representative, as one of 2 EDS representatives. So I have an abstract that's been published. I like to include abstracts in my talks so that I can later look at it and say, okay, what was this one about? And so that people who look at them, I send them to them, they have a clue what's covered. What I'm going to be talking about is some of the motivators. Oh, this is a little not quite right. I'm going to focus on superconductor electronics. And there's a little tiny bit on quantum information processing and the technology roadmap that if I'm fast enough, then we can talk about it at the very end, but I will probably skip that. Okay, motivations. Why are we doing this? A little bit of history. Superconductivity was discovered in 1911. So it's been around for a while. And you compare that to some of the, like for semiconductor electronics, the junction type transistor was invented 1948, so later. But there's been a kind of a parallel path of what's been going on. And it was only in 1962 that the switching device that we use for superconductor electronics, the Josephson junction, was first developed, or even theorized first. And by the way, for those of you who are graduate students and don't know, Brian Josephson was a graduate student who theorized that there would be this thing called this Josephson junction, and the leaders in the superconductivity field told him he was crazy. Well, he ended up getting a Nobel Prize. So anyway, some things have been progressing since then, but there was a time in the 1950s even when superconductor electronics and semiconductor electronics were neck and neck, and it was not clear which one would win. Well, semiconductors clearly won out and have led things for quite a while. Okay, well, why should we re-look at things again? I'm gonna go on. Well, this is one example. Now, this was from back in 2013. There was starting construction of, this was a Facebook data center. They were going to build their first data center in Europe. They, at that point, they had ramped up to the point they had so many users in Europe, they couldn't support them all from the United States, the data centers in the US. So they went to look at Europe, and they found this place, Luleå, Sweden. It's near the Arctic Circle, average annual temperature 1.3 degrees Celsius. You get a little free cooling. It's right near some major rivers that have excess hydropower. And they looked at it. So that's where they built it. The problem is that this doesn't really scale. There are not enough places like Luleå, Sweden, to build all the data centers. And this has just continued over time. And now, especially that AI is really taking off, the power demands are huge, power and energy. Okay, so we got a problem, and we knew that over 10 years ago. We started looking at superconductor electronics. And as I'll talk later a little bit, switching energy is low, ability to move information is even more energy efficient. And we just looked at the numbers and we said, okay, it looks like, especially for large scale applications where you get really energy efficient refrigeration, there could be some huge, on the order of a factor of 100, improvements in energy efficiency for computing. Okay, and that launched this particular effort. There was an effort run out of IARPA. It was called the C3 program, Cryogenic Computing Complexity. But being IARPA in places like DARPA, you had to have an acronym. So it was the C3 program. And maybe a little aside, so when I was involved in selling that program, and this earlier graph here, this did not communicate well to the people who had money with, just determined funding. They didn't look at this and feel like they had, it was compelling. So if you're going to be looking for money or you're trying to sell an idea, you need a killer slide. This was our killer slide. This, and that's Obama standing there in front of this, what was then the largest supercomputer in the world at Oak Ridge. And it was like, okay, here we have, this is the existing technology, and people knew what it was like. At that time, we had a huge problem that I think it was in northern Maryland. The energy grid, the power grid was maxed out, and they couldn't add a new big computer in that area without unplugging something else. So people knew that there was a problem, and we said we can do it for on the same order performance with more memory and much less, so a factor of 100 lower power and smaller. Now that was a projection, and that was the motivation for going and doing this. Okay, looked interesting. Then there's also been efforts in quantum computing. D-Wave is one system. This is a commercial system that's available. And it's currently the system with the largest number of Josephson junctions, these switching devices that I know about, it's just a little over 1 million junctions. So we're still a long, long way from a real supercomputer. You think about what you can do with 1 million transistors, FETs, not very much. You know, your phone has billions. So we have a long way to go, but it looks on energy basis like it's a promising technology. Okay, quantum computing, you maybe see in the pictures where people have these, you know, lots and lots of wires going on down into the cold space. That's not going to scale. And people are looking at moving some of the control and readout circuitry down into the cryogenic space. If I have time, I'll talk about that. So what's our vision? That in the future, large scale computing, we don't care, we no longer care what technology gets used as long as it does the job best. And we're looking at putting together lots of different approaches, hybrid technologies for computing. Okay. So that's quick on the motivation. As far as the roadmap goes, technology roadmap, there used to be a ITRS, International Technology Roadmap for Semiconductors. And that went until about 2013, and then that stopped. And what changed is that we no longer care if it's semiconductors. It doesn't have to be, we can do photonic computing or quantum computing, we don't care. We just want to do computing. And that's when the International Roadmap for Devices and Systems, it's an IEEE group, formed. And when they formed, I said, hey, now you're open to anything. What about superconductors? What about cryogenic electronics? What about cryogenic CMOS? And they said, sure, come on in. And after a short, I think it was a couple of years, they said, okay, we'd like you to become an international IT technology, international, well, we're an international team, IFT, an international focus team. So I now run a team of, I think it's close to 30 people internationally who contribute to these reports. Okay. 2023 is our current, our latest published report. And main areas of coverage, superconductor electronics, that's what I'm going to focus on for the rest of my talk. And we have partial roadmaps, cryogenic semiconductor electronics, and then quantum information processing. And 2023 was the first year that we included that was the first roadmap for superconducting quantum computing. That's a challenging thing because we don't really know how to build a quantum computer. So building a roadmap for something you don't know how to build is a little challenging, but it's a technology roadmap, how we see things going. Okay, so that's available. It's on the web. You just do IEEE IRDS, you'll find it. And especially for graduate students, if you were looking for a literature search, maybe that helps. It's got maybe over 1,000 references, and it gives you pointers to what's going on in different areas. So it can be a good overview. This is the report in the section on superconductor electronics. We start with applications and market drivers. The new approach to this technology road mapping is we look at the, what are the needs? What are the applications? And what are the market drivers for these applications? And what do we need to satisfy? And so that's top down, and then also bottom up. What can we make? And how can we pull these together? And one interesting thing is that quantum computing has become an application and market driver for superconductor electronics. Okay. Status 2023. It's still a developing technology. It's got a small market. Yes, it has a big promise, but it's still a very small market compared to semiconductors or, or conventional microelectronics. It's a tiny market. Quantum information processing is an emerging driver, and logic, as I'll go into a little bit more, is there are many competing approaches. And memory, we have very little memory, and there's a huge need. Fabrication, and I'll be talking more about that. There's mostly research fabs and a little bit of commercial fabrication capability. Key needs, we got plenty of key needs. Power supply, I'll talk more about that. Figuring out how to make these things less sensitive to the environment, magnetic fields, currents, trap flux. We need to make them much smaller. Current technology node is minimum feature size on the order of 250 nanometers, which is huge compared to, semiconductor CMOS. Fabrication for scale, that's what I'll be focusing on. Okay, but that's the kind of thing that the report is designed to talk about. Logic. So we're still in the process of what I call searching for the winning combination. For those of you who don't remember, back in the 1960s, semiconductor logic, there were several different logic families that were all competing. And I'm seeing a few nods back here, from people who have gray hair like me. So yeah, there were all these different approaches, but by the especially later in the 1980s, it had come down to CMOS. And CMOS was not the best in all ways, but overall it had the winning combination. And a joke at the time was that CMOS does nothing well. And that was partly because there were other logic families that did certain things better, and also because what it was really good at was it didn't dissipate a lot of power when it wasn't doing anything. So, but it was the winner. And, it has done remarkably well. Well, where are we now? We're in the 2020s. And we've got all these different logic families, and it's not clear what the winner is going to be. So we're sort of in a Precambrian explosion of circuit. It's a circuit. There are people who like to work on circuit implementations, and they're having it's a fantastic playground because they're developing all kinds of new circuits and trying to see how they can bring them together and find some winning combination. So part of what we do is we look at these different approaches and we kind of rank them, and we're trying to guide people towards certain approaches. The devices per ampere that you can support is kind of low, like 10 to the 4th devices per ampere. For a cryogenic chip operating at, say, 4 kelvins. So in liquid helium environment, you really don't want to supply even an ampere. So if you can't support more than 10 to the 4th, 10,000 devices, we give that a red. Like, no, that's not going to work. You need approaches that have much more capability. And we're trying to guide people towards what is going to be useful. Memory, we also have monitor memory. We really need better memory ideas, and we really need things to come up. The numbers of, these are bits. This is not gigabytes or terabytes. These are bits. And the numbers here for developed memories are small. There are ideas for coming up with much higher things, much higher numbers, but ideas and reality are, still far apart. Benchmarking metrics, that's one of the things that we've been doing. The question is, how do you compare something that operates at, say, 4 kelvins compared to room temperature? And we've come up with methodologies for comparison. And that involves looking at cryogenic refrigerators and looking at the specific power, how many watts it takes at room temperature divided by the watts of cooling that you get at low temperature. Okay, and we don't even know why it has this relationship. I mean, here's the Carnot. You can see that it's far different from Carnot. One important thing is, so here for liquid helium, typically it's on the order of 10,000 watts per watt for small refrigerators. We call cryo coolers, things that would be on like a cryo pump, that sort of thing. And then large refrigerator systems, more close to 1,000 or 500 or something like that. And the way that we do things is we say, communicate with the median and then the range, rather than picking any one number. But one thing I want you to see is that for people who want to operate at low temperatures, millikelvin temperatures, like quantum computing, look at the number here, 1 billion watts per watt. That should tell you that, okay, if you want to dissipate 1 watt at 10 millikelvins, 20 millikelvins, then you've got to supply, you've got to provide a nuclear reactor or some really big power supply to power this thing. That's a challenge. So that tells you that you really need to be energy efficient if you are going to operate in the millikelvin temperature range. Okay. I'm going to quickly just say, we look at switching energies. Switching energies are on the same order as competing other technologies that use semiconductors and other things. Fine. Where we really win is, and I'll just go, there's a couple of ways that we look at these things, but we really win in energy and in data movement. If you have to move signals around, you've got superconducting transmission lines, and let's see, the benefits are on the order of, for energy, thousands of times better, and for delay, hundreds of times better. So that's in the benchmarking. We also look at fabrication processes. Most of these are what are called research fabs, some Lincoln Laboratory in the US. There's a couple of Star Cryoelectronics that's very small. Seek here in New York does some fab, their commercial fab. We try to monitor what these different fabrication processes are and where they're at, what level what they can do. So commercial, yeah, we have some commercial processes. We develop a roadmap. The key thing that I will mention is that one thing that we're really interested in is when we can go to modern tools, which are like 300 millimeter tools. And the question is, when do we have to have our processes ready to go to 300 millimeter? And right now it says 2028. I think that's going to be delayed. I don't see us hitting 2028, but that's an open question that we need to work out. But we try to give the community some sense for what they need to be ready for and when. Okay, conclusions. The key thing I'm going to talk about is, okay, we do have logic. We're still searching for the winning logic family, because I'm going to be talking about fabrication, and fabrication and the logic go together. because the logic depends on certain devices, and the devices that you make, you have to be able to fabricate them. And fabrication technology, as I said, well, minimum feature size, only about 250 nanometers. We need to get below that. And we're still also searching for a winning fabrication process. Okay. I'll talk a little bit about the approach, the dominant approach to logic. There's more than one way, but this is the dominant approach to digital logic using superconductor electronics. And I say it's a primer intended for circuit designers. I know that there's some people in physics here. You just hold your nose. I'm not going to be talking about Hamiltonians. Okay. Josephson junction, basic physics. What do we have? We have two superconducting regions, and in a superconductor, the electrons, they don't exactly pair up. They don't pair up. It's a collective phenomenon, but this is a simplistic picture that you have these, you have a collective behavior here, and you have a wave function, and they can tunnel from one side of this barrier to the other. So that's a Josephson junction. And there's a current phase relationship. So the more current you push through it, the phase goes up, up, up until it reaches a maximum. This is a sinusoid. And then it drops. And so what happens is, if you've got a junction and you got a little current through it, and you add a little bit more current and it pushes it over its limit, it goes through this this little jump. We call it a phase jump. And there's an analogy that physicists like to use about a pendulum with damping. If you are really familiar with the equations for pendulum and pendula and damping, you can look at it and say, okay, yes. So that's an analogy. You can take these junctions. Now, let's see, I'll talk about how this is a circuit model for this junction. There was a question earlier. We have this Josephson junction. This is the new symbol. It's now an approved international symbol for the Josephson junction. And this is the model. And here's a phase-dependent current source, which is a standard symbol. So how does a junction switch? I was talking about how you'd have a, there we go. A current can flow across this junction with no voltage, and it rises up to the point where it hits the critical current. If you're looking at current and voltage instead of current and phase, this is what it looks like. It goes up, and then, oops, it jumps over to this branch out here. And let's see if I got, yeah. And then if the current goes back down, typically it'll get stuck at some low, at some voltage that's greater than zero. And they latch up. There was a time when IBM, back in the early 1970s and early 1980s, was trying to use these to develop computers. And they were trying to use these junctions like this, and they latched, and they kept having problems. And for a variety of reasons, they stopped that effort in 1983. Okay, well, after that time, there was a group in Russia that figured out that you could take these junctions and put a shunt resistor around it, change the dynamics. And the way that worked is that the current would go up, and instead of latching, it would jump over and then would come back. It was little or no hysteresis. And when these things switch, they develop a little voltage pulse. The voltage is quantized, or the flux is quantized. So if you integrate the voltage over time, you get a flux quantum. So it creates a little flux quantum. And there are benefits to this. One thing, it's quantized. You get a quantized output. And it doesn't latch up. There's a variety of, so this is what initially in the 1990s really pushed superconductor electronics forward. How do these little junctions work? So I talked about the pendulum analogy. The other analogy is that these junctions are a little bit like a baby drinking milk. Take a baby, take a bottle, put milk into the baby. The baby is happy as long as the flow is low enough. However, if the flow is too great, the baby spits up. And that's what a Josephson junction does. So, you put a current into the junction and it's going down this way, fine. Too much current, it spits up, and it spits up one flux quantum at a time. So, so my apologies to the physicists, but for circuit engineers, it's like, oh, okay, the current goes in this way. If it's too much, boom, I get this little kickback. Great. Okay. What do actual circuits look like? Because these are quantized in flux, current times inductance is important. Whereas for semiconductor circuits, it's all about charge and charge and voltage. For us, it's currents and inductances that are important. And this product needs to be about one flux quantum. So this is what a circuit might look like if you looked at a side view. So you've got a bottom layer of superconductor and a top layer, and in between you have these little vias, and you've got some insulator in there that make the barrier. And so you've got, between these two layers, you got little loops. And we supply a current to bias these things, and that's what a circuit would look like. Okay, I'm not going to really do it. There are challenges, but that gives you a sense for this is very different from semiconductor electronics. And there are a variety of circuit families that have been developed. I mentioned that current is a problem. There was the early approach was you supply a bias current to these junctions and you use resistors to distribute the current. Works very well. It dissipates power. About 90% of the power that this circuit uses is burned in these bias resistors. Well, that doesn't scale. So there are people who have been developing other circuit approaches that, and these are only some of the ones that are over 10 years old. People are developing much more effective and efficient ways. We're still looking for, the circuit implementation that will really do everything. I'll talk a little bit more about that later. Okay, circuit innovation right now. So an example, I'm going to talk about this is one particular logic family that uses majority gates. Sometimes the gate sets are very different in superconductor electronics. And that can be challenging for the electronic design automation tools that have been really focused on the needs of CMOS, and where you have NAND gates, for instance. And you have a particular gate set, can use very different gate sets. Important thing is, here's some examples of these majority gates. They've been coming down in size. But when you compare them to CMOS, we're on the order of 25,000 times less dense for a gate. Okay, majority gate, you can do a little bit more computing with a majority gate than you can with a NAND gate, but still, there's a huge gap. And even if we look back at when both of these technologies were about the same fabrication minimum feature size, there's still a gap of 60x. So we look at where does that come from? And we look at, these are CMOS NAND gates, what's going on there, where our differences are. And we find, yeah, there's roughly a factor of 60 difference. And a lot of it has to do with this particular logic family relies on transformers that don't scale down very well, and inductors and devices that are inherently larger. Another problem is that Josephson junctions are 2-terminal devices. FETs are 3-terminal devices. You can do more with an FET than you can with a 2-junction. You need more Josephson junctions to do the same logic typically than you do with transistors. So we need to reduce that, and we need to make things smaller. If we look back at, this is Gordon Moore, when he looked at, this was in 1975, and he looked back at some of his projections and how things were going in 1975. And his analysis that the contributors to making things denser or more complex circuits, die size, making bigger dies was one contributor. Well, we've kind of run out on what, well, there are people who are doing like huge Cerberus, and they're doing an entire wafer as, a processor. Yes, you can push that in some ways. Dimension reduction, that has a contributor. The biggest contributor back then was what he called architectural cleverness. So this is, there's plenty of things for the circuit guys to do, circuit people, designers to improve the technology. So yeah, we're looking at a combination of what can we do to improve things. There's a list of stuff. We can increase the number of wiring layers. We can get rid of the inductors or reduce them. We can replace inductors with Josephson junctions that have inductance with them. We can make the Josephson junctions smaller. We need to be working on all of this. Oh, let's see. But that doesn't mean that there's not a need for your contribution. There's a need in all of these areas, and we need solutions. I think I'm going to quickly, I've mentioned DC supply current, bias to the junctions. There are some logic families that you got a Josephson junction and you want to bias it. And so you supply a current to bias these things. And this is just talking about how, okay, you've got, how they work, how they switch. But if you run some simple numbers, in this case, you got a million junctions, and they typically operate about 100 microamps each. You quickly get to the conclusion you're supplying 35 amperes to a chip. That just doesn't work. So that kind of limits you to less than 1 million junctions. And that just tells you immediately that that's not enough current, that's way too much current, not nearly enough junctions. Traditional DC biasing will not scale. So part of our message is telling people, okay, great, you can make these little DC powered circuits. It's a dead end. You gotta be working on AC power. There's a reason that power delivery, the power network in the United States and elsewhere is AC, not DC. So we've got to switch how we power our circuits. And that's because this SFQ approach is about currents and inductances. It's not voltages. Like CMOS has a great advantage of supply voltage. That's not a problem. We need currents. We need a better way to do that. We got to go to AC. Here's an example of an AC powered logic family. There's been some publications, very interesting approach, and very different gate sets. Here you have an OMA3 gate where you got 3 inputs and you have 3 outputs, and the 3 outputs you get an OR, a 3 input OR, 3 input majority gate, or a 3 input AND gate, all from the same gate. Well, for people who are looking, used to traditional logic gates, it's like, wow, what is this thing? How do you use it? What can you do with it? How does that, what's going on? And you've got all these little transformer things in here. Wow. Okay. I want to see it. I want to see, right now it's what I'll call PowerPoint engineering. And we need to see some real results from this group. This is a group out of IMEC. Very interesting approach. They say that they can get, significant real memories finally, 30 gigahertz throughput. They have some impressive numbers. It's like, yeah, okay, show me. I want to see. Many questions. Yeah, we absolutely need demonstration. There's another family of AC powered logic, some very interesting. This is a group that's led from SEEK, that's in to New York, closer to New York City. And they say that they've come up with an approach that has a power supply that uses AC and only supplies the makeup energy that's required and no more. It's patent pending, and so they're not publishing until they can get their patent, but there are several people who are very interested in how this works, and we want to understand what it is, because that would take care of some of the power supply needs. Not the logic, but the power supply. Yeah, we're waiting for details. Okay, I've been talking about these traditional Josephson junctions, but there's other kinds of Josephson junctions. And there's different flavors. What I was talking about was this sinusoidal current phase relationship. They're called 0 JJs. They're ground state. They will sit in with 0 phase shift. There are other things called pi JJs and phi JJs. There's this whole family, and people have looked at these and said, look, if we could make some of these more interesting junctions, rather than having a complex circuit block that takes a lot of area and multiple devices, you could get it down to just one device. So that's why I say one junction to rule them all. Maybe we can get there. So there's people working on new devices and how we would put these devices together, and yeah, can we fabricate them? That's the key questions. One group that I've been associated with at University of Southern California has developed a new logic family using 0 JJs and pi JJs. I was talking about using current to bias the junctions. Well, another thing you can do is use junctions that have a built-in phase shift, these pi junctions. And if you combine them, rather than needing a bunch of inductances and other things, you can just stack junctions, and you have, this looks more like traditional CMOS, where you've just got a bunch of FETs and they're all just wired together. So this looks very promising, but to do this, we're going to need to develop a fabrication process that can supply both regular Josephson junctions and pi Josephson junctions. I'm going to talk a little bit about the fabrication process. So what do we need? So we could look at all of this stuff and we say, what do we need? One thing is we need a thermal budget comparison compatible with CMOS back end of the line. CMOS, the wiring layers, all that kind of thing, you can use up to 400 degrees Celsius roughly. Right now, we don't have that. We have a much lower back end of the line. Our processing temperatures have to be kept lower. And so we cannot take advantage of all of the things that have been developed for CMOS, for gap fills and everything else. That needs to change. We need to be scalable to smaller sizes. We need junctions that can be made smaller. We need a stack up. It would be nice if we had a stack up containing both junctions. Maybe there's ways that you can only do one junction. It might be nice to have both different types of junctions. And it'd be nice to have capacitors for AC power distribution. You can do things with capacitors. Capacitors scale down better than transformers. Okay. What's done now? There's a process that uses the dominant process for digital superconductor electronics, uses niobium as the metal. So you got some niobium here. And then aluminum gets deposited on top. And then the top, say, nanometer of aluminum gets oxidized in a chamber, and then you deposit niobium on top. These have been dominant since maybe the 1980s. And they're almost good enough, but they're not going to take us forward. That's my take on it. Part of the problems, you have niobium, columnar grain growth, they're rough surfaces, and I'll show more in the next slide about that. You get cracking at via edges. The aluminum oxide is just a mess. It's amorphous, but it just got all kinds of things going on in it, and it's just not controllable. And if you get really thin, trying to make things thinner than 1 nanometer controllably is tough. And the temperature limits for the niobium and the aluminum oxide, it's less than 200 degrees Celsius. So that makes any other processing, you gotta figure out low temperature processes. And that's just that's a pain, costs money, takes time. Anodization, that's not a process that's you take the wafer, you put some electrical clips on it and you dip it in a bath and you anodize it. That's not something that's done in commercial production. And we got to get rid of it. So, variety of reasons. So let's see. We do have. This is an example of surface roughness. We've scanned the surface roughness, and I'll just make the comment. This is the surface of the niobium, and if you run these statistics, you get some numbers like the RMS surface roughness is 1.2 nanometers. Well, maybe that doesn't sound so bad, but if you look at the range, 9 nanometers, and then you look at the picture and you say, okay, well, how many times do we have, like, here's a high spot, and then there's a low spot, and they're pretty close together. You get a sense for, there's some serious variation here that looking at RMS numbers really hides, okay? I've just come to the conclusion that we're not going to take this to the finish line. We got to find something else. So people have been looking at other approaches: niobium nitride, niobium titanium nitride, and part of the group here at Cornell is looking at these and saying, well, there's some problems with niobium nitride. We really ought to focus, we think, on niobium titanium nitride. It's got some good benefits, higher critical temperature. It can work, we can use temperatures up to 400 degrees Celsius. That's not a problem. It has some challenges. The coherence length, the distance within which superconductivity can be destroyed is on the order of 5 nanometers. That means that interfaces are very important. You have to have good, clean interfaces. And that's, so it's more challenging with niobium nitride or niobium titanium nitride. So we're working on a process. We are developing a process. It's like going back to the drawing board and saying, okay, what materials can we use? How can we do it? Things have come a long way from the 1980s. I know because I was there. You know, I was depositing films and we were doing it blind. And like today, I was in some of the labs and looking at things, and you got tools that you can see what you're doing as you're doing it. It's so much nicer. Well, we hope that that's really going to help because we need a better way to do things. Okay, this is another fabrication stack that's been proposed by IMEC Group, and they've got everything that I was on my list except for Josephson junctions. But it looks promising. There's some questions about what's going to go into the barrier and how you can make these things uniformly. There's still plenty of work to be done. A chunk of this work is being done currently at Albany. I don't know what's New York creates, or what do you call it? The Albany nanos?
Yes, is it creates.
In New York, okay, so they changed their name and but anyway, it's that group over in Albany, and they're working at some of its 300 millimeter scale. I think I'm just gonna skip some of this. People are doing development of, like, this is niobium nitride. Group in China, they're making some interesting progress, but I look at this and I look at this area where, like, here's the corner and I see a lot of cracking, and we need better ways to deposit. This indicates to me that we need better ways to deposit the films. Yeah, and let's see, I'm gonna skip that. So there are people looking at, okay, we got these nitrides, what kind of barriers can we use? What are the candidates? DJ is one of those people who's been looking at that kind of thing, and the groups here. We're trying to figure out what combination of materials is going to get us what we want. And getting the right crystal structure, there are ways to, you can either heat the thing, or there are other ways that you can add energy to a growing film to get the structures that you want. And so we're looking at a variety of deposition approaches. And over the last couple of days, I've talked to some of you about what have you got? What ideas are there? How do we do this? You know, what are the tools? And here's a few that I've seen elsewhere before coming here. We're trying to figure out what's the process that we can use to fabricate these controllably. Okay. And one thing is that I'm looking at a technique called reactive high PIMs, high energy, let's go back here. High power impulse magnetron sputtering. It's like sputtering, but you're using pulsed power, pulse techniques. It takes all of the variables that you have in magnetron sputtering and then adds more. And the problem is there's just so many variables. And I talked to people, I was like, okay, can we use convention? Can we use machine learning to help to guide what we're doing? And the answer was, well, you need 1,000. How many thousand data points can you give us? 50,000 would be really nice. For anybody who works in materials development, when they say 50,000 samples, it's like, I'm never gonna get my PhD. I can't, you know,
Every day.
even if you're, well, it's just too many. So I have found a publication where people are looking at, they've looked at reactive DC magnetron sputtering and with titanium nitride, which is pretty close to niobium nitride. And they're using training sample counts from 5 to 40. Well, that sounds really promising. I hope we figure it out. And I've been talking with people here who work on machine learning and AI guided materials development. We're going to need that to help us figure out, find our way through this vast, variable space. Okay. I think pi junctions, I'm going to skip this. There's ways to make pi junctions. An example, there's a superconductor niobium nitride. If you put a ferromagnetic material or there's a variety of ways you can do it. There are different barriers. You can create these pi phase shifts. There's a variety of approaches, ferromagnets, ferrimagnets, unconventional order parameter symmetry, non-equilibrium electron distribution. There's a variety of ways that people can make these things. You can use high temperature superconductors and geometry to create these things. Here, D wave, S wave, ramp, zigzags. There's a variety of approaches. We need to find a way to make these pi junctions. That is under development, and that's what some of the people, even in this room, are working on. Okay, conclusions. I'm just going to say that we've got a situation where there's an opportunity. There's a wave coming. There's an opportunity wave. And for anyone who has any experience and knows anything about waves and catching waves and surfing, you have to be in the right place at the right time. If you're not, like this person was here, able to catch this wave, if you're in the wrong place, you watch the other people go by. And that's kind of what happens sometimes in technology waves. When things are coming, you gotta be prepared, you gotta be ready, you gotta be able to catch the wave. And if superconductor electronics doesn't catch the wave, then it'll be photonics or some other semiconductor thing or who knows what. But, and the wave may pass. Okay, so good luck.
Well, thank you for this wonderful talk, but now you have time to ask questions, ask hard ones. Farhad.
You have this interesting technology map in the beginning where you mentioned that superconductor really had the advantage in the interconnects. And the logic seems to be, scaling down much better with the voltage of the charge. So what about these hybrid systems where you do logic with the normal charge and voltage, but you replace all the interconnect with superconductors?
Where do you know where the energy goes in those interconnects? In standard integrated circuits, where's the energy dissipation? Do you know?
Both in the metal and the drivers.
Not only in the drivers, but in the metals, like you're charging up a line and then you're discharging it, right?
Throwing it in the ground.
Yeah, okay, and that's where the big energy is going. With superconductor electronics, with these single flux quantum, there are these little pulses that are on the order of couple of picoseconds wide. They're these little voltage pulses, and these things go ballistically, so its speed of light in the medium is on the order of c/3. These little flux quantum go speeding down these transmission lines. So rather than bring the whole transmission line up to half a volt or almost a volt, right? And then discharge it, and you have 1/2 CV squared. That's where the energy is going in transmission. So you get a little benefit because the resistance goes down, because that's 1/2 CV squared is but there's a resistive component as well, especially when you get really small wires.
Well, that's what I meant actually, just send those pulses in, but with the normal semiconductors and not superconductors on the two sides.
So how are you gonna generate these little pulses? You can use standard semiconductor logic. You're gonna be charging up the lines and discharging. So the 1/2 CV squared is gonna remain. You'll get a little benefit on the resistance, and that might be helpful. And so people are looking at that for like quantum computing using spin qubits. You know, people are looking at, how do you put these these interconnects together? But for a regular computer, not enough of the energy is in the resistance. There's too much in this 1/2 CV squared, charging the line and discharging. And so you're not going to get as much benefit as you would like. Okay? Another one.
Amit,
You have this chart of you need a megawatt for a watt.
Yep. Or 10 to the 9th watts for at 20 millikelvins. Yes.
But I have two questions. First is if you were trying to computer in space, does that get alleviated? And then why is this ever gonna work? That's the
Well, space is a problem that, so the background temperature of space, about 3 kelvins. So it looks like, oh, that's great, I'll put it in space. But space is also a good insulator because it's vacuum. And you get some radiation. But radiation goes as T to the 4th power. And if you're sitting at 3K or 4K or 10K, to the 4th power is not a very big number. It's hard to get rid of the energy in space. So your thing is sitting there, sure, the background is 3 kelvins, but it can't radiate, it can't convect, it can't, it can't get rid of the energy, so it heats up. So space doesn't really work. You have to have a refrigerator even in space. You do get some benefits, but yeah, it's challenging. And so
The second one was like,
why would this ever work?
yes. Well, why, I mean, obviously it's very important because you're giving a very good talk and it's super amazing, but it can't just be a sandbox. Like, what is the thing that will make a difference?
Okay, quantum computing is one potential where if you're going to be operating at 20 millikelvins anyway, and you've got the refrigeration already there, and you need associated circuits around the qubits. You need to do classical computation around the qubits to control them, to read them out, to do things like decoding of errors. And if you've got those things, you want them to be as close to the qubits as possible without disrupting them, so that they, because you can't afford the delays. You can't afford to send things up to room temperature for processing, and you can't wait. The qubits are decaying over time, and you don't have a finite time to get your computation done.
So let's say a decoder needs to decode a 3-bit number to 8 control lines. I'm saying,
okay, just a second. When Amit asks a question, can you please repeat the question? Because I'm afraid that people sitting in the back cannot hear what Amit is asking.
So the question was decoding? What the heck is that?
well, I mean, I'm just saying, let's just take that as a very classical thing that you do in computing. N by N qubits, you gotta take some number of bits, you gotta decode that. So the speed of that, you're saying is gonna be somehow faster using some
Superconductors can be very fast.
Okay,
So you can operate, like the IMEC approach, they're talking about running things at 30 gigahertz, 50 gigahertz. Yeah, we can run things fast and low energy, but you just don't want to be sending signals very far because we're limited by the speed of light. So we need things to be close. And if you need it to be close, that means it's going to be in the cold space. So people are working hard now on cryo CMOS for quantum computing. And the challenge, cryo CMOS. If you're going to operate CMOS, at 4K, for instance, it's going to dissipate power. And so if you've got two different technologies that are already going to be at 4K, then these, superconductor electronics are like 6 orders of magnitude lower energy, power. So that's where you get the real, that's gonna, you think, be the first step, the killer app that if we can do it, and then prove that, then you say, oh, okay, how do we scale this up to make a supercomputer? We'll see.